So resonant pulse inverters. Last time we discussed pulse width modulated inverters, which are the basic type of inverters, and we discussed how to convert a DC voltage into an AC voltage, but that AC voltage was a square wave. And then we also saw that if we have RL load, inductive load, then the output voltage and current um, can change, especially the current can change slowly, because of course the inductor resists the change of current. Anyways, the other type of inverters, and there are some drawbacks of resonant pulse inverters, as you can read over here. Since when the current is changing in in the pulse width modulated inverters, it is going from high value to a low value. Hence, in a very short amount of time, and actually is instantaneously, hence the rate of change of current is very large at switching, and hence it increases the switching losses. And at the same time, um, your switches also go through a high voltage stress because of that. In pulse resonant inverters, that's not the case, because the idea of the pulse resonant inverters is, if you remember from circuit analysis, resonant circuits, RLC resonant circuits. So the idea is, if you have an underdamped RLC circuit, we know that the current of that underdamped RLC circuit changes based on the frequency of the sinusoid, changes something like that, exponentially decreasing sinusoid, and if you have a step function, then it will be something like that. It's gonna go to a steady state value. So for resonant pulse inverter, the idea is that if we can capture, let's say, if we can capture this thing right here, this is almost sinusoidal waveform, half of the sinusoid waveform. It is of course affected by an exponential decay, but again, if the frequency of this sinusoid is much larger than the rate at which it is decaying, then when we catch this, it is not a lot of it's not going to be a lot affected by the exponential decay. So the idea is to create an underdamped circuit such that when we activate the switch, it is going to create a sinusoidally exponential waveform, and as soon as it hits zero, let's say only this, as soon as it hits zero up to here, let me show up to this point, then we turn the switch off, and then when we turn the other switch on, which will let the same waveform go in the opposite direction. So that's the basic idea of resonant pulse inverters. So again, from circuit analysis class, if I remember, that was chapter number 7 and chapter number 8, if I remember correctly, one of the chapters that we discussed RLC circuit, resonant circuits, and RLC parallel resonant circuits. So there are three, when we discuss RLC circuit, if you remember, there are three things that that are associated with the circuit. You have the Napier frequency alpha, you have the resonant frequency, which is omega naught, and then if it is an underdamped circuit, then you have a natural resonant frequency, omega n or omega d, and in the book actually it's represented by omega r, which is the square root of omega square minus alpha square. And if you forgot about it, just open your circuit analysis book, chapter number 7, I guess, and then go through it. So the idea is that we create an RLC circuit, L, C, and R circuit, such that when we operate the switches, it will create an underdamped pulse, not underdamped pulse, sorry, sinusoidal exponential pulse from this underdamped circuit, and we can capture that pulse in both direction, in the positive direction and as well as negative direction, and from that we can create an inverting circuit, a DC to AC inverter circuit. So that's the basic idea of series resonant inverters, and it's a very commonly used circuit. So the basic requirement of the circuit is that your circuit has to be underdamped. The other requirement is generally we want the Napier frequency alpha, which deals with the exponential decay. The natural frequency, the Napier frequency, we want it to be smaller than the resonant frequency omega naught, because if it will be much smaller than, then of course the natural resonant frequency is going to be quite higher than alpha, and it is going to oscillate many times before it goes down to zero. In this case, we don't want it to oscillate many times. We just want to capture each oscillation, that is the oscillation in the first cycle, and that will be repeated in the second cycle, and so on and so forth when we keep turning the switches on and off. So let's discuss, in your book there are like about 8 different circuits that they're discussing under series resonant circuits, series resonant inverters. In the lecture notes, I'm just going to discuss four circuits, and all these circuits basically are part of series resonant inverters. And so let's look at the first circuit, series resonant inverters with unidirectional switches. These switches can be MOSFET, can be thyristors. We're going to discuss thyristors in the next chapter. Can be thyristors and can be BJTs or any other power switch. So the idea over here is that, of course, it's an underdamped circuit. Omega naught is greater than alpha. That is 1 over LC. Alpha for series RLC circuit is calculated by R over 2L. So this condition must be met. And in general, omega naught we try to keep quite larger than alpha again, so that we have a good sinusoid. It will not be damped by the exponential function greatly. So there are different modes of operation for this circuit. The first mode is when Q1 is fired, Q1 is activated, and Q2 is off, and we call it mode number 1. So what happens, the circuit is going to look like this. So the current is going to flow from the source, Q1, L, capacitor, resistor, go back to the source, which is this circuit, a series circuit. So if we calculate the value of current here, again, go back to circuit analysis. It is a step function, or so we need the complete response of the current, and that response is simply the steady state value or the final value plus the natural response. Now, the final value of the current is going to be 0 because it is going to produce one pulse or half pulse or half sinusoid, sorry, one pulse. So at the end of the pulse it is going to be 0, and at the beginning of the pulse it was 0. So the final value of the current will be 0 because actually let me go back. If you keep operating this circuit, then of course the capacitor is going to be fully charged and there will be no current in the circuit. Hence the final value of the current when time hits infinity is going to be 0. So that's the final value we have to put. So it's going to be 0. So the current will only be comprised of the natural value. So I1 is equal to IN, and for underdamped circuit the generic expression for the response, natural response, is e to the power negative alpha t, a cosine omega nt plus b cosine omega nt. And if you remember how did we used to find a and b in circuit analysis, there were 2 things that we need to do. The first thing is set the initial condition for I. So at time t is equal to 0 or 0 positive, we set the initial condition for I, and as I just mentioned a while ago, at the start of the cycle, let me go to the waveform. At the start of the cycle and at the end of the cycle, both current is 0, of course, because we are only capturing, remember what, one pulse of that underdamped waveform. So since current is 0 at the beginning of the cycle when time t is equal to 0, when we put t is equal to 0 over here, then cosine of 0 is 1, sine of 0 is 0, exponential is going to become 1. So a is going to be equal to 0 again because current is 0 at the beginning of the cycle. That means current will only be b e to the power negative alpha t sine omega nt, which is the expression of the current in the first mode. Okay, now when this, so initially capacitor has some voltage, before the cycle is started, that is from the last cycle. Now when the current will keep on flowing, capacitor will start charging, and at the end of the cycle, capacitor will have a voltage, what we are calling VC1. It will have a maximum voltage of VC1. And when the cycle started, actually it had a voltage what we are calling negative VC, and we're going to discuss negative VC in a little bit when we discuss the mode number 3. So that's what's going to happen in the first mode, that current is going to be B e to the power negative alpha t sine omega nt, and the capacitor will be charged to VC1 such that the positive polarity of the capacitor is on top and the negative polarity will be at the bottom. Let's discuss mode 2. So now based on what type of switches you're using, if you're using very fast switches like some of the MOSFETs, then you don't have to wait a lot before turning Q2 on and when you turn Q1 off. Now if there are sometime you use a switch that is that takes some time to turn off, the turn off time is significant, then of course you cannot turn the other switch on in the meantime. You have to wait until Q1 completely turns off. So generally, based on how fast you're turning the switches on and off, again you don't want this switch to be on when this is still operating. So this is still turning on, turning off, and you turn this switch on, then it's going to be a short circuit at the output. So you don't want that. So generally it is possible that we will have to wait for a little bit before we turn switch 2 on. So during that time there is really no current in the circuit, and we call this time the off time, or call it a dead zone. When both the switches are off, we call it dead zone, and the dead zone depends upon the turn off time of switch number 1 and switch number 2. So if there is turn off time of switch number 1, sometime some microsecond or nanosecond, then we will have to wait for that time. At least at the least amount of time is going to be the time it will take for the switch to turn off. And if we want to be on a safer side, then we will wait for perhaps few microsecond more and then turn the switch to on. So that time is called that time is when everything is off, and it is called dead zone. So there is nothing at the output, and during that time capacitor is going to hold on to its maximum voltage VC1. It's not going to let it go, of course, because there is no other component through which capacitor is going to discharge. Now when after dead zone, what's going to happen is we are going to turn switch 2 on. So Q1 is off now, we turn switch 2 on, capacitor has voltage. Now the source get disconnected from rest of the circuit as soon as you turn Q1 off. So now what's going to happen is Q2 is on, capacitor has voltage, so capacitor is going to start dissipating its charge through this loop. So it's going to become this loop right here. So it's going to become a natural circuit, a source free circuit, which is shown. This is node 2, this is shown right over here. So it's going to become a source free circuit. And in the source free circuit, of course, there is no forced response or steady state value is 0. So I3 in this case, the current 3, and observe the direction of current 3 is the opposite, because when capacitor will start discharging, it's going to discharge from the top. So the direction of the flow of current is going to be different than what we used to have in mode 1, and that's why the output is going to be bidirectional or AC. So current direction is going to be opposite, capacitor starts discharging, and then it will discharge to 0, at which time inductor will be charged, store energy in this magnetic field, and then rest of the time inductor will start supplying current until the current hit to 0 again, at which time capacitor is going to be charged in the opposite direction. So positive is going to be here and negative is going to be here. Positive will be here and negative will be here. So capacitor is gonna change polarity, and it will have now voltage in the opposite direction, and that voltage we call VC. And on the graph it shows negative VC because our polarity, positive polarity, is when capacitor is positive on top and negative at the bottom. So now capacitor is positive at the bottom and negative on top at the end of mode 3. So let's go back. I3 is this, and of course again we do the same thing to find C and D. First we put the initial value of current 3, which of course is 0 at the start of this cycle. So we keep we make C 0, and then D sine omega t e to the power negative alpha t is going to be the expression of I3. So the expression for both are same. Of course we will have to figure out what is the value of D in equation number 6, equation number 4, and then B in the last equation of the current in I1. As far as waveforms are concerned, these are the waveforms. G1 and G2 are the gate signals if you're using MOSFET, or the base signals if you're using BJT, or gate signal again if you're using thyristors. So G1 is activated for Q1 in the first half of the cycle, for first T1, what we're calling the time T1 or T1M, and then we have the dead zone when both the switches are off, and then we activate Q2. So this will be the current, although they are showing quite sinusoidal-ish, but it is exponentially changing. Sinusoid, it is quite close to sinusoid again, as long as your exponential frequency, alpha and upper frequency, is quite smaller than your omega naught, or smaller than omega naught, then it is going to be quite sinusoidal, as you will see in one of the examples that I'm discussing. So this is your I1, then you have dead zone, no current, and this is your I2. This time is T1 or T1M as they're calling. Tm is the time at which the maximum value of current happens. So this time is T1 right here, Tm, sorry, right here, as it is shown over here. Dead zone time is either T2, you can call it T2, or we are calling it T off. There is no current here. And then mode 3, the time is T3M, and T3M and T1M are similar to each other because the waveform is going to be exactly same. Why? Because the circuit, natural circuit in mode 3, and the forced circuit in mode 1 both have the same RLC value, so it is going to have the same type of response. Capacitor voltage, VC1 is the peak value which it will hit in mode 1. In the dead zone it will keep that value VC1, and then mode 3, capacitor will start discharging, start giving up its charge, and then inductor starts charging the capacitor in the opposite direction right here, and then the value is going to be negative VC. The minimum value is going to be negative VC. Now the question is how to get the exact expression of current and voltage, that is how to find the B and D for the currents in mode 1 and mode 3. So we already used one of the initial conditions. Now the other part that we used to do in circuit analysis is to take the derivative of current with respect to time, and then analyze that at the start of the when the switch is changed, or when the switch is condition on the switch is changed. So we take the derivative of I1 with respect to t. This will be the derivative. We evaluated that at the start of the period. T is equal to 0 positive. Now we know that from circuit analysis and the basic relationship of inductor current and voltage, that VL is equal to LdI over dt. So we use that over here. VL 0 positive over L, B omega n, and then VL from the circuit is Vs minus Vc minus Vr. And we know that since at the start of this term at 0 there was no current, so the voltage on the resistor will be 0. Why? Because of course resistor voltage is I times R, Ohm's law, and I was 0, hence VR will be 0. So the value of B will simply be Vs minus Vc0 positive over omega NL. And what is Vc0 positive? Remember, capacitor voltage does not change instantaneously. So what is Vc0 positive? Negative Vc. At the start of this cycle, the value of capacitor voltage is negative Vc right here. Let me grab this. This is easy to make circles. Okay. So I1 is Vs plus Vc over omega NL e to the power negative alpha t sine omega nt. That's the equation for I1. And we find the peak time at which I1 will become maximum by taking the derivative of I1 and equating it with 0, because of course at the peak your slope of the curve is 0. So to find the peak value, we find first, we take the derivative first and then equate it with 0, and from there the peak value, the time for which the peak value will occur is going to be this. And when we plug this in this equation, then of course we can find what is the peak value of I1, and this is done in example number 1. Capacitor voltage, again we find the capacitor voltage similarly. VCT is the final value of capacitor, steady state value plus the natural response. The final value, if you let the circuit go back to the circuit again quickly. If you let the circuit go, of course, the final value of the capacitor voltage is going to be Vs. So that's Vs. And then of course natural response, as we did for current, e to the power negative alpha t e cosine omega ntf, this. So to find one of the variable E or F, first we're gonna put the initial condition Vc0 positive, and Vc0 positive is negative Vc. So we plug this negative Vc over here. Let me delete this over here. So negative Vc is equal to Vs plus E, because when you put t is equal to 0 positive, of course cosine becomes 1, sine becomes 0. So this E is equal to negative Vs minus Vc, negative Vs minus Vc. And to find the value of F, again we're going to differentiate Vc with respect to t and evaluate at t is equal to 0 positive. And you can see the derivation over here, as we did many times in circuit analysis. dVc over dt, again use the capacitor relationship, IC is equal to C dV over dt. So from that, dVc over dt is IC, and of course since it's a series circuit, IC is the same thing as IL. And at the start of this this section, or start of this time period, of course current was 0, inductor current, so we're gonna plug 0 over here, and from that we can easily find that F is equal to this. So we go ahead and plug the value of Fs over here as well, and then simplify it to get the capacitor equation, this. And we do the same thing for mode 3 for the natural response, and you're gonna get I3 equation this, where the constant is this, and Vc3 equation this. Okay, now we have to find out the exact values of Vc and Vc1. And to find out the exact value of Vc and Vc1, we're gonna use two equations. Equation number 8, which is right here, Vct, and equation number 11, which is right here. So this Vct is right here. It's Vc1t, actually equation number 9 and equation number 11, I would say. So this is the voltage in the first T1, and this is the voltage in the time T3. So we're going to use these two equations, and from these two equations, after some manipulation, Vc will be equal to Vs over e to the power alpha pi over omega n minus n, and Vc1 is this. And we already know the values of Vs, that's the source voltage, alpha of course we calculated, and omega n we calculated, so we can easily find Vc and Vc1. Also, if we add Vc and Vs, then you will see that that will be equal to Vc1. which implies that the current that is given in 6 and current I3 which is given in 10, they are the magnitude of those current are exactly the same. Why? Because I3 is VC1 over omega NL, and go back and check I1 is Vs plus Vc over omega NL. Vs plus Vc is Vc1, and you can again use these and you can show that when you add Vc this plus Vs, you're gonna get Vc1. So I1 and I3 are exactly the same, except of course I3 is in the opposite direction. Now we can also find out what is the maximum possible frequency of the output that is possible with this series inverter, resonant pulse inverter, and that we utilize dead zone. If TQ is the turn off time of the switch and T off is the time of dead zone, then T off has to be greater or at least equal to TQ. Now what is T off? If I go back to this and try to explain it, I don't know how many of you will understand it. Alright, remember that omega n is the frequency of this. If we let this go, then omega n is going to be the frequency of this waveform. This is half of the waveform. Now remember, omega n is what? Omega n, oops. Let me see. Let me read this real quick. Omega n is what? Omega n is 2 times pi times f, right? F of n, the natural frequency, whatever you want to call it, which is equal to 2 times pi times the time period of that, t of n, let's say, right? And since this is half of the waveform, so omega n, the total time period is Tn. This is the total time period right here. So this is Tn by 2. This Tn, this is Tn by 2. So when you calculate that, the time which is here, right here, which is T1 time, then that is going to be, oops, too far, that is going to be pi over omega n right here, pi over omega n. So this time is going to be pi over omega n, because the total cycle length is 2 pi. Remember, one cycle, right? 2 pi. So this is pi. So that's going to be pi over omega n. So that's this time right here where my mouse is, and then this time is half of the output time period, right? The total time period is, let me go to comment, grab a line, total time period is this right here, right? So that's half of the time period. So that half of the time period is pi over omega out, half of the time period, because the total time period is going to be what? 2 pi over omega out. 2 pi f is omega out, f is 1 over t out, so t out will be 2 pi over omega out for the total time period. But since this is half of the time period, of course, that means is pi over omega out. So this is the total dead zone time, pi over omega out minus pi over n. This is pi over omega out right here, and this is pi over n right here. So that difference between the two is the total time, and that is going to be should be greater than the turn off time of the switch. So you manipulate that, and then you will figure out that the output frequency should be less or equal to 1 over 2 TQ plus pi over omega, And the maximum output frequency, of course, has to be when you have the equal sign, which is this. So that's a description of the basic resonant pulse inverter. What is the advantage? Of course, we discussed the advantage at the beginning. It reduces switching losses, which are associated with large rate of change of current. But of course, it has the harmonic problem. Why? Because you have discontinuity in the output waveform when you have the dead zone. Now, based on your switches, you can reduce that discontinuity. If you choose very fast switches, then that discontinuity can be reduced, and you have a very low harmonic. There will still be harmonics, but there will be very low harmonic problem. So next, we're going to discuss example 1 in the next video.